All right. I think we're ready to start. So people are still joining, but we'll just go ahead. So thank you all for joining today. My name is Karim Masloud. I'm the manager of international projects at Premier Corex. I'll be your host for today. So we are very pleased to relaunch this series of webinars. We originally started during COVID, and it was, I think, well received. And due to popular demand, we're reinstating it back. So the session today marks our inaugural session presented by Jules Reed. Jules is our VP of Operations and our Technical Global Director. Okay. And if you're first time attending, welcome. We hope you find this helpful and insightful. If you have joined us on one of our webinars before, thank you for coming back. And again, we welcome you. Okay. So Jules will explore the significance of the advantages and disadvantages of Sidewall core. These are the key takeaways from today's session. Okay, a little bit of biography about Jules. Jules, can you move to the next slide, please? Yeah, thank you. So he has over 35 years of experience. He's the co-author of the textbook on core analysis, best practice guide. Okay, Jules is also a former president of the Society of Core Analysts. Is currently sitting on his technical committee and a peer reviewer. Okay, he is expert in most aspects of core analysis, particularly on wettability, capillary pressure, relative permeability, and EOR. Okay, Jules, thank you very much for presenting today and for the valuable information that you will share with all of us. Please go ahead, start.
Thank you for the introduction, and it's a pleasure to begin these sessions again. As Karim said, today we're going to look at sidewall core and what value there can be from sidewall cores, and how it might compare against standard coring and standard core samples that are obtained after coring. And titled it Sidewall Cores, a Sideshow or a Core Contender, just because I like to be a little bit, I like the alliteration of that, and I like to be a little bit contentious sometimes, just to get people thinking. So what we're going to look at today, as an overview of things, we'll look at the acquisition methods of sidewall cores. We'll look at some of the advantages or challenges that there are to the different sidewall core types. And then I'll look at some examples of sidewall core samples, and then begin to look at the sidewall versus full diameter question, and then finish off with some summary and the conclusions. So there are these days potentially three types of sidewall core. There's really only two, either percussion or rotary. But within the rotary, you have the original rotary size, which was approximately 1 inch in diameter, and then you have more recent large rotary. When I say recent, at least 10-15 years. Large rotaries sometimes gets called max core or XL rock, and they would be 1.5 inch in diameter. And the whole reason of going to those larger cores was because the amount of material acquired from the 1 inch samples and the potential for damage was quite large. And so the higher volume large cores were a better addition at getting closer to what a standard core analysis core sample would be. This is showing you from Halliburton's systems just a schematic of the old percussion sidewall core system. Basically, as part of the tool, a downhole tool, you would have this gun body. Within that gun body, there would be explosives placed behind several small core barrels. They're called core barrels, but they're just a cylinder that gets fired out into, so this is just showing you the blow up of that. The explosive charge is set off. That will fire at the particular depth of interest. That will fire the barrel out into the formation and capture whatever rook system is there. So it's a bit like a bullet or an empty bullet firing out into the system and capturing some material. Now those samples, as you could potentially imagine, have possible issues, except where you're in soft sediment. If you're in more consolidated systems, then those samples often could come back with some fractures. And so quite often the porosity and permeability are over optimistic on those systems, and they're often used for merely just looking and verifying the formation or the lithology of the formation that we're currently in. So that's percussion. But then as technology improved and we're able to put rotary systems downhole, then the process moved into rotary. And I've got a video here that came from Schlumberger showing you the rotary sidewall system. So this anchor shoe comes out to push the tool against the surface. Inside you have a core bit, which is currently in vertical position. It then moves into, well, perpendicular to the tool. You then also these days have core markers, which can be placed between the different samples that are taking, because one of the issues of early systems is if a piece of core was not obtained, you weren't sure which cores were obtained and which ones weren't. So you couldn't always tell what depths the samples are coming for. But now with the core markers in place, it separates out the samples. And if no sample was acquired at a particular depth, then you'll have an empty space between two different markers. And so the depth control becomes more accurate, or the correlation of core sample to depth becomes improved. So this is the process of taking rotary cores. This is from Halliburton's system. There's the tool out of the actual coring piece outside of the tool. So that will be pushed out into the formation, acquiring the samples, then angles it down, and the samples then begin to build up inside the tool with some core markers in between each samples. And this one is showing 1 inch. So this is the standard 1 inch rotary size. But these days you can also get the larger XL Rock or Max Core 1.5 inch diameter samples. And some of the considerations here, some of the differences between full core and sidewall cores. One, when we're acquiring full core, the full core is being cut around or inside the drilling bit or coring bit. As you core down, the core is being pushed up inside the core barrel, and so the core becomes contained in the core barrel, and once it's in the core barrel, it's less exposed to the mud system and to mud invasion, because inside the barrel you then have a relatively static system of the fluid. So any mud cake that's built would be now static in place, and that will reduce the potential invasion. And particularly with low invasion coring systems which are available. And if people are interested in that, we gave a a webinar right at the start of this whole webinar series several years ago. I can't believe it's like 4 or 5 years since we started that. However, for the sidewall cores, one of the potential issues with sidewall cores is that they are obtained from the wellbore face. And the wellbore face is being continually exposed to a moving mud system, or potentially moving mud system. Yes, a mud cake will build, but the shear forces of the new mud system itself could begin to remove portions of that mud. You then have higher potential for invasion into the sidewall cores. There's also, depending on the mud balance, whether you're significantly overbalanced or you're close to balanced in the coring process, that's also going to have a bearing on the properties of the sidewall cores potentially. So if you have significant overbalance while you're acquiring the site during the drilling, then there's the potential for fracturing or higher invasion. So looking at some of the advantages and challenges with different sidewall core types. So we've got the percussion type and we have rotary type. And this information came, some of it, from a recent BP presentation at LPS, London Petrophysical Society this year. In percussion sidewall cores, so some of the advantages of percussion sidewall cores is that they generally can have higher recovery rates in soft sediments, soft rocks. Rotaries in soft sediments can be quite poor. Maybe not acquiring core, or maybe or acquiring smaller diameter than is expected, or smaller portions than expected, because of the softer and more potentially more fissile nature of the core that it's drilling into. For both percussion and rotary, there can be a selective post-drilling sampling, so that from the wireline process you can get your formation data, and then choose your sampling points where you want to take those samples, depending on when the sidewall core process is acquired. It's done generally alongside wireline, so it's part of a potentially part of a wireline tool. And the percussion process is a fast acquisition process. So of all of the coring processes that are out there, percussion sidewalls, rotary sidewalls, or full diameter core, the percussion sidewall core is the fastest method of acquiring core material, and it makes it a good advantage, particularly in exploration processes. And so that you can have quite a lot of these percussion guns, the percussion barrels within a tool, and so it can allow for a potential large number of percussion samples at relatively low cost. Of course, there's always a cost, because there's the cost of tripping in, stopping at each of the depths that you're requiring, and then tripping back out again. And generally the percussions, because you may not be so particular, because you've got more samples, you may not be so particular about the exact placement of the sidewall location. You could just shoot them bottom up relatively quickly at roughly the proportions or positions and locations that you require during the pull out of hole after the wireline process. And in general, it's a simple tool and pretty reliable. The challenges of percussions, though, are that the samples may be damaged by the borehole impact, extraction from the bullets. The depth control is less accurate than the rotaries, and there may be invasion from, as discussed earlier, same as you would have on rotary sidewall cores. They tend to be just the 1 inch diameter, so they are small. The samples then tend to be irregular shaped because of it's not actually acquired by cutting, it's by firing the bullet into the rock formation. And so that can be challenging for rock property interpretation. It's also going to be, you're going to need permissions for having explosive at well site. And so that could be an extra cost or extra administration to deal with there. As with all sidewall cores, the orientation of the core is not guaranteed. It's always going to be perpendicular to the tool. And so depending on dip at that point or the angle of bedding, or if you're in a high trajectory well, then acquiring horizontal and or vertical plugs can be challenging or impossible. And particularly vertical plugs, unless you're in a fully horizontal lateral well in a horizontal system. And generally, you're going to have limited volume of plugs. And as was stated by this BP presentation, not really enough rock for the life of a field, for appraising a field. Rotaries. Again, you can have selective location control. And because in the rotary system, it's a much more involved system, you've got control of the tool to go from vertical to parallel to the tool to perpendicular to the tool before it starts plugging. You've got extra time there for that to happen, and so you're going to need slightly more time than the percussion system, but you can actually pick your spots more accurately then. It means that generally there are going to be fewer samples, and so you need to be more selective about where the sampling is. Now that, as well as the percussion can be, but the rotaries in particular, because you're acquiring samples from specific points that you think are going to be describing at least the major points of interest in the reservoir, you may be missing sections of the reservoir or understanding of the full lithology of a system. And so you could have quite biased sample sets. Also, there can still be poor recovery or issues of recovery, particularly in soft rock or fractured and fissile, like shales systems, or where you have high permeability and a higher overbalance of the mud system, significant invasion and fracturing caused by all the mud invasion. And some of the other processes that you're able to obtain from standard core, where because of the low invasion, you potentially have fluids present which are still representative of the reservoir system. Quite often in the sidewall cores, you can't do any analysis of the fluids in place. So with standard core, we can acquire samples from the center of the core and perform analysis of the fluids, which quite often can be very representative of the reservoir fluids, where you don't have any data or any information about the reservoir fluids, particularly water and water salinity. However, it's much more difficult because of the high levels of invasion to perform that on sidewall cores, whether percussion or rotary systems. The tool is more complex, and so there's potentially more challenges with that. Although the technology has improved greatly over the years, and I'll show you some examples of some very high quality cores that have been taken. But again, similar to the percussion systems, the angle of acquiring core samples is very dependent upon the orientation of the tool and the dip or bedding that is in place. And so very often you may not always get horizontal, or what we call horizontal, which is parallel to bedding, or perpendicular to bedding. You can sometimes be left with samples that are somewhere in between, oblique to bedding, and still similar to the percussion, and potentially even less rock material for the life of the field. So those are some of the challenges to overcome. The handling of the data can then be a bit more complex. So here's to show you some samples. I'll start off with some what appear to be very good samples. This is actually on ResearchGate. You can find the paper for this. It's from Task Frontera. I think there are well over 100, maybe 150 sidewall core samples. You can see here, these are the XL rock. So the diameters here were about 3.8 millimeters. 3.8 centimeters, 38 millimeters. And you can see these are, in general, there's a few where you haven't got full acquisition of an actual plug sample. But in general, you've got pretty good quality of plugs, except some of them, because you've got no control on where you're taking the samples. You have ones like this where the bedding is oblique. So you can see that this is starting off roughly halfway and tapering out. Now, that layer there is going to be a barrier to flow. So when we try and do permeability analysis of this sample, we're really only flowing through this portion, maybe through this portion of the sample. And so the length area criteria of this sample are not really the measured length area of the sample, and that can introduce some level of uncertainties. And the level of uncertainty really depends on how much of a barrier to flow this layer is, how much that is crimping out to the end of the sample, etc. You've got then this sample as well, where you've got dual bedding, cross bedding. You've got one type of rock type at the top of the sample, a different rock type here below the sample. And so this is probably going to be tighter at the top, and all my flow is going to be through this sand unit at the bottom. And so again, the actual measured area of flow will not relate to the actual flow area. And so it requires some more complex interpretation to understand really what the flow of this rock type is. And then in here, you've got, again, some kind of dual rock typing going on. You've got some mudstone or shaly system at this top, and then you've got this more sandy unit here at the bottom of the sample, and it's going to be uncertain how that will impact. And then you've got these two samples which are just very short, and so there's going to be issues obtaining much data other than potentially lithology out of these two. As well as that, this sample here is actually fractured. You can just see it there in this picture, but taking an axial photo, you can see the fracture there, and it runs throughout the sample. So yes, we can get porosity. Permeability of this is going to be challenging. Again, this sample here had a slight fracture, but you can see that it's very highly laminated. However, this is potentially representative of the reservoir layers at that area, and so could be useful. But you can also see in here the slight oblique bedding as well, and so there may be more uncertainty in interpreting the data for this sample. And then this sample here was also fractured. So in general, a lot of the samples were very good, but still there's at least 8 out of 18, 45% will either have limited use or some challenging interpretation. So 55% of the samples pretty good, 45% of the samples may be challenging to interpret and or use. Here's some other ones. This is MSCTs, which stands for Mechanical Sidewall Coring Tool, but these are samples acquired by an MSCT, both taken in white light and UV. So from the UV, you can see where you've got hydrocarbon shows, liquid hydrocarbon shows, but you can also see that there's, again, some pretty good samples here. These are 1 inch in diameter, but you'd still also have somewhere you've got fracturing, and that's going to limit the length compared to area calculations, because when we get into measuring permeability, there are certain length area criteria that you want to try and obtain. So it's always best to have at least 1.5 times the length compared to your area. But some of these are going to limit that. This is some other ones. This was again from this was a Patel report on the Wallula basalt formation. Out of these 4 cores that they're showing, 1 is fractured. These are 1 inch cores again, 1 inch sidewall cores. This one's fractured. This one you can see has a significant heterogeneity. This one has fractured here at the end. You're going to have to trim this down to here. That will be a very short sample, and so reduces the potential testing you can perform on it. And this last one is a very good sample. So here you can see the wide variability of potential acquisition from the sidewall cores, and the need to assess each sample individually. What we don't see on here as well is potential, although we can see macro fractures, it's very difficult to understand whether there are microfractures present, and microfracturing could easily be happening because of the mud weight on the systems. And so we would generally recommend doing CT scanning of any samples, but for sidewall cores, one of the things that may be very useful is to actually do micro CT analysis, which allows us to see, and still may not be high enough resolution to see all microfractures, but will allow us to see more evident microfracturing that could be in samples. So it's a recommendation for all sidewall cores to go to micro CT scanning. However, that significantly increases the cost of and obviously timing of a project, because you know, taking the sidewall cores in the first place was to try and reduce the costs that come from coring, but that's potentially going to increase the costs for testing. This was another. These are all available online. This was from the paper the journal Environmental Geoscience, volume 27. You can see here on these 4 samples, one sample this is carbonate system. One sample is pretty reasonable, but the other 3 samples here, this is undercored, so smaller diameter than was acquired. It's also very rounded, so quite irregular shaped. This one here is showing, you can easily see the fracturing here. And this one has significant stylolites running through the sample and is potentially fractured along some of those stylolite bands. for these cores, they're excellent for looking at the lithological description, looking at XRDs and describing the pore system that's present, but they're going to be relatively limited usability for general rock properties. And depending on the quality of the sidewall cores obtained, that's a general rule of thumb. They're going to be excellent for lithological description and things like XRD, petrography, but could have limited usability. So let's look at then sidewall cores versus full diameter conventional core systems. So looking at the cost of acquisition, a sidewall core's generally going to be around about 100 to 200,000 US dollars in an offshore system. A full diameter core for say a 20-meter core could be more like 200 to 400,000. Taking the rough average of those, 150,000, you would acquire generally a rotary sidewall core around about 30 samples maybe. So that would be 5,000 US dollars per sidewall core sample. Now, in a 20-meter core, you could take as many samples as you like, but on average, taking 4 horizontals per meter, generally within that, and 1 a vertical, generally going to be somewhere around about 140 samples. You'll take some for Dean Starks as well. And so that's going to be about $2,000 per sample. Or if we look at it in terms of weight of material acquired, this will acquire about 4 kilograms of core material. So 30 samples of XL core or max core XL rock would be about 4 kilos of core material. So that's $37,000 per kilo of core material. Whereas in a full diameter core, you're looking at that would, at a 20-meter core, would be approximately 360 kilograms of core material. That's roughly $800 per kilo of core material. And having the full core allows you access to that core over time. You would generally take preserved sections so that you're preserving sections for later analysis, allowing you to keep coming back to the core and performing additional analysis where it might be required. And so a full diameter core allows you access throughout the field history. Whereas the sidewall cores, they're generally going to be a one use, because quite often a number of tests that to be performed on them could be destructive. Those tests have to be left to the end of testing, but then you've destroyed the sample, and you don't have that sample remaining, and you've got a limited number of samples for testing. In a different BP presentation, but from the same LPS earlier this year, BP did a similar look at the value of core, and they used this equation here. We called it RVC ratio. So recovery, volume, and the cost of different core types. So this RVC is the recovery times volume divided by the cost. And they presented this table here showing you then a normalized ratio to the percussion sidewall cores. So they see the percussion sidewall cores as being the least value, but still valuable in certain circumstances, particularly in exploration and soft sediments. But compared to sidewall cores, the rotary sidewall cores would be 3 times more valuable than a percussion. But core itself, they reckoned to be nearly 800 times more valuable than percussion sidewall cores, and available throughout the life of the field. So sidewall cores were best for exploration, or where you have no information, and for understanding initial properties and gaining a quick understanding of the properties of a system and the field and rock types. But sidewall cores and can also be used in certain situations where it's been difficult to obtain core, and so allow you to still access core material where you might not be able to get full diameter core. Some of the other challenges with sidewall cores come on to then program timing. So what I'm showing here at the top is number of weeks and the number of weeks for a standard special core analysis program using standard full diameter core samples from a full diameter core. So we have an initial preparation period. We've got cleaning and drying, saturation, standard permeability. Then you might do some mercury injection capillary pressure, which gives you pore size distribution, gives you lots of information very early on about the core, but is contaminated by mercury. Now, in the full cores, we can just obtain offcuts of the samples and put them through the mercury injection. But with sidewall cores, we don't have that option. Any mercury injection has to wait to the very end of testing. I've not shown it on here, but it's basically after week 65 here. What you can also do with these a standard coring program, core analysis program, is you obtain samples from similar rock types and you split them into different batches because you've got 140 samples to handle if you've got 20 meters of core. So you can put 10 samples through electrical properties and capillary pressure, another 10 through cation exchange capacity or understanding clay typing, another, say, 5 through centrifuge capillary pressure, and 5 into relative permeability. And so that whole program, these can be anywhere between 20 to 30, maybe could be slightly more than 30, depends on sample numbers and the equipment availability, but maybe 30 weeks. But with a sidewall cores, each sample, because of limited use, quite often you're having to reuse the samples. And that one sample might have to go through capillary pressure, then through the cation exchange capacities or C0, CW, then through centrifuge potentially, and then through rail perm. And so it significantly extends the timing of any core analysis program. So that has to be taken into consideration when looking at sidewall cores. The timing required to obtain data will be significantly longer potentially. BP showed this as a sidewall versus full diameter of what's available, what type of testing is available, and what type of testing might not be available. So they show here that conventional cores can be used in just about anything. There is some areas, so reservoir fluids, you can perform analysis. There can be some uncertainty, particularly if you've had any type of invasion, but you would test for that. The acquisition and placement or sample bias could still happen in conventional analyses if you're overly considering the good parts of the rock. So you really need to do a statistical sampling process rather than just a biased one. But in general, almost any program is available in conventional core, but with sidewall cores, there can be that sampling bias because you've pinpointed the particular areas of interest. There's limited sample volume. There's limitation to the orientation that you require. There are then limited sedimentology because you're only getting the sedimentology of the samples you've acquired rather than the full distribution of the interval, depth interval of your reservoir. You can't really then do structural geology, and you really can't really do the reservoir fluids. but all the other data is potentially available, but with some possible uncertainties, additional uncertainties around interpretation of certain test types, particularly capillary pressure and relative permeability and electrical properties. So you need to be a bit more careful of using the data from sidewall cores. So just as a summary process, you can still get good consistency from sidewall cores. These are data showing resistivity index, capillary pressures. So the capillary pressure from, say, an air brine porous plate in the blue, and the red is from mercury injection of similar samples from the same test. And you can see some similarity. You can also see the mercury injection is lower. That's expected. You often need to make corrections to mercury injection data, which will shift the saturations here slightly to the right and make it align more with the SCAL data. So there's good correlation between, in this particular case, between the two different data sets. However, there can still be some challenges where you have some wide variation of data. So this is showing you relative permeabilities performed on sidewall cores, rotary sidewall cores. There's a wide variation of properties here. And it's difficult to know whether the variation is coming from heterogeneities or degradation, because throughout the program, if a sample is having to use in electrical properties, then in centrifuge properties, then in relative permeability, in each process, it could be degrading because you're applying stress, you're de-applying stress, you're reapplying stress, and so on. So you maybe get hysteresis happening. And so the wide variation is difficult to begin to understand whether that's coming from heterogeneity, whether it's coming from slight, small degradation of properties each time, small plastic regime rather than fully elastic, whether it's a function of rock type, or whether there's been sample damage, or because of mud invasion, whether there's been wettability alteration that has is challenging to understand and potentially challenging to remove. So in conclusion, sidewall cores, particularly rotary sidewall cores, can be very useful, especially during the exploration process of a field, when there is a still large uncertainty in the formation properties. There can be more uncertainty in sidewall core data compared to conventional cores. That could create a more uncertain interpretation process. The cost per volume of material is significantly greater in sidewall cores than conventional cores, although the physical cost immediately when you obtain the sidewall cores is lower, about maybe half the price, potentially less than half the price, but roughly half. The cost of each individual sample is greater. And the sidewall, and so as an overall, sidewall cores, are they just a sideshow or core contender? Well, they could be a core contender, but it really depends on your usage and requirements and the quality of the sidewall cores obtained. So with that, I think we open up to any questions.
Jules, thank you very much. We have questions in the Q&A section. If you can address them, that'd be great. Thank you.
Okay, I'm not seeing the Q&A in the chat or in the unanswered questions.
In the chat,
no?
Yes.
In the chat. I'd opened the Q&A portion. Okay, I will have a look. Okay, so one question: why not doing MICP at the end of all of the tests on sidewall cores. I did not see it in the test recommendations Excel chart. It was there. I didn't put it on at the end. I would do the MICP at the end as well, and so it would extend the 65 weeks that was showing there into 68 weeks. But the mercury injection would have to come at the end, because once you've done mercury injection, that's destructive tests. They're contaminated with the mercury, so you couldn't really do any more tests on there. One of the what makes MICP sometimes very useful is you do get lots of early data, which allows you to design your tests better. And so it can be very useful to get mercury injection early in a test program rather than at the end. And quite often the MICP is used to have early data and an early capillary pressure estimation. So having it at the end of all the testing sometimes defeats the whole purpose of having the MICP in the first place. And two, what's the minimum dimensions on sidewall core samples for rel perm? If you have a 1 inch, if you can perform rel perm on 1 inch samples, the 1 inch sidewall cores, if it's a rotary, can sometimes be 2 inches long, and then you've got 2 inch versus 1 inch diameter. And that can be a very good dimension. In general, you really want the length of the core to be longer than the diameter. So if you've got 3.8 centimeter diameter, you want at least 4. That would be a bare minimum, and really you would want longer than that. Another question: globally, have you come across pressurized sidewall cores which have been used for reservoir saturation analysis, such as Dean Stark? Yes, I didn't mention it here. It's relatively recent, but I'm not sure what the costs are. I've not been involved in one directly, but I know that they exist out there. I'm trying to remember the name of it now, but it has a specific name. I'll see if I can find it and we can put it out. But basically, yes, it acquires the cores and it keeps them in a pressurized cylinder, bringing it to surface, and so you can then depressurize once the tool is at surface. And any comment on the results quality? Yeah, well, I've not been involved in that, so I'm not sure. But it's like anything. All of the sidewall cores are coming from the wellbore region. The core is trapped internally, as inside the barrel, whereas the wellbore has been exposed to all of the shear and filtrate loss of the mud system. So the saturations there could need some could be difficult to interpret. It depends on the mud system. So it depends what the mobile fluid is, whether you're in a transition zone or immobile water. It really heavily depends on the whole process of both drilling and then acquiring the rotaries. Any preference to use sidewall cores rather than softer or stronger formations with regard to recovery? I think I mentioned earlier that rotaries are good in consolidated systems. The percussion sidewall cores are better in softer sediments. Would you recommend sidewall coring on unconsolidated sandstones, even if drilling a wildcat? in a wildcat system, you know nothing. So if it's or relatively nothing, if it's an unconsolidated system, taking the percussion cores is reasonable. What it does is it fires out the bullet, retracts that back into the system, and it's sitting still inside of the bullet itself. So rather than the rotary where it drops it down, drops a sample down and actually pushes the sample out, and so then they would get mixed if it was soft sediment. In the percussion system, they should be still contained in the bullet. So I'm just reading down the session. Okay. Sorosak from PTTP. Thank you for a great presentation. A question about MICP on samples below 0.4 cc's of pore volume. Should we proceed the analysis on those samples? It really depends on, so below 0.4 cc's of a pore volume, this is probably referencing our book, below 0.4 cc's of a pore volume, you begin to get more and more uncertainty in the data. If you don't have any other samples and any other data, then of course the MICP process is going to give some data, but you have to widen your potential uncertainty on that data. So it's either, do you acquire the data and have at least something, even though there is some uncertainty on that, or do you do nothing and have no data and basically guess your properties? So I can't answer that. That becomes a value decision for yourself on whether you need the data or not, and if you it can improve your model by having at least some data, then it's potentially worth it. And the mercury injection is quite cheap. And two, if we cannot get 1 by 1 inch dimension of a core plug, can you suggest the minimum sample size below 0.4? So this, again, I've sort of answered that. If it depends on how much samples you have and how much is available, but you can have less than the 0.4, but I would begin to put more and more uncertainty on it, on the outcome. Why MICP results should be calibrated with other results? That's a good question, Ahmed. So the MICP results, you're injecting mercury, which is non-wetting, into a vacuum, which is obviously non-wetting. There will be some gas molecules. So you're basically injecting mercury into gas, where neither of the fluids are a wetting fluid. And so it's not truly a wetting phase process, and capillary pressure is about wettability. Wettability controls capillary pressure. And so plus the mercury, because it's a large molecule with very high interfacial tension, as it pushes into different minerals, different clays that are potentially present in that sample, it can begin to damage the clays. And so quite often the mercury results overestimate the amount of mercury that can be injected, because it's potentially damaging the sample as it injects, and it's into total porosity rather than effective porosity. And so quite often that you need to adjust your saturations, one for the fluid phases that you're injecting into, but two, to adjust for wettability and immobile fluids, and effective versus total porosity. Okay, I think that's all of the questions. If I've missed any, I will apologize now, and maybe hand back to Kareem to finish off the webinar today.
Thank you very much, Jules. That was fantastic. Very much appreciate the knowledge that you've shared with all of us here today, and thank you for it. For all the people who joined us today, thank you very much for your time and joining us. We very much welcome you. We will. The session was recorded, so we will share the recording with you all. Please, if you have any further questions, please feel free to reach out to Jules or to ourselves through the sales@premiercars.com email. There is going to be another session held on the 2nd of December, as long as this series will be hosted by our very own Lee Wright, and it's going to be also focused on the value of the proper core preparation. So please join us for this session as well. We'll try and continue to host these sessions every 3 weeks on Tuesday at the same time. So just mark your calendar, and we would love to have you with us. Okay. Again, thank you all for joining, and any questions, just please reach out. We're one click away from your email. Okay. Thank you very much.